My name is Eduardo Julian, and today I want to talk to you about a programming language that I created and I have been working on for a little while now called Lux. So first, a little bit about myself. Basically, I am a programmer from the Dominican Republic. I work mostly on backend software, mobile, and Internet of Things. I've been working with several languages, mostly Clojure, JavaScript, Java, since around 2010. And basically, I'm just a big fan of programming languages, paradigms, abstractions, and especially Lisp and functional programming. But that's enough about myself. Let's talk about Lux. What is it? So basically, it is a purely functional Lisp that draws a lot of inspiration, mostly from Haskell, ML, and Clojure. From Haskell, it takes a lot of the pure functional feeling and semantics and some features here and there. From Clojure, a lot of the syntax and overall look and feel for the language. And from ML, a lot of inspiration for polymorphism and its module system. And I'm actually going to touch on a little bit of that later on. I also want to stress that Lux is not a research language, and it's also not a hobby language. It is a language that I'm making for practical purposes for day-to-day programming. And precisely because it is meant for practical purposes, one of the things that I want is for Lux to target multiple platforms. So currently, for version 0.5 of the language, it already runs on the JVM and Android devices. And coming soon for the upcoming version 0.6, there will be a brand new JavaScript backend. So you will be able to write nice client-side code in Lux and even be able to share libraries across your front-end and back-end if they happen to both be written in Lux. Lux has static types, and it's not optional. It is a mandatory static typing system with type inference, as you can expect from modern languages. Several types of numbers, strings, tuples, some types or variants, as they are also known, records, and of course, universal quantification or parametric polymorphism, as is also known, and existential quantification. And it has many really cool features. So one feature that it has is FirstClass Modules. This actually ties back to what I said previously about Lux inheriting from ML. So ML has what is called the modules system, which is basically the way it does polymorphism. Basically, things are separated in two kinds. You have signatures, which are like interfaces in other languages. You define your methods and constants and whatever in a polymorphic way. And then you have structures, which are implementations of those signatures. So for any particular type, you implement the structure, and that's what you use for polymorphism. But something that sets Lux apart from other languages in the ML tradition is that Lux modules are actually first-class values. What it means is that they're values like any other. You can store them inside variables, store them inside data structures, and you can even pass them around in functions, which is great for composition. For example, in this slide in the lower left, there is actually a function that, given equalities for two different types, it actually builds an equality for a tuple of those types, which is a very simple thing, but it's really nice to be able to do. And another example on the right, is building equality for lists on top of equality for the individual elements. This is very powerful because, for instance, in other languages in the ML family, you don't really have that flexibility. Modules are a second-class citizen, but in Lux, you have all the flexibility that you get with your normal values. Something else that Lux has is great support for concurrency. So personally, I believe that nobody really knows how to do concurrency properly. There are many approaches, many techniques, but ultimately, it is up to the programmer to truly decide what is the proper way to write their concurrent code. Some languages want you to focus on particular paradigms. So maybe one language focuses on actors, or maybe focuses on software transactional memory or FRP. In Lux, I wanted to provide options to people and leave them with the decision of what is best for their system. So Lux has great support for promises, which are, by the way, monadic, as you can see from the slide, which is great because that way you can write nice code that seems synchronous, that seems like normal sequential code, even though behind the scenes everything is working asynchronously and taking advantage of multicore. You have functional reactive programming. I apologize that the example is not particularly exciting, but the slide was already a little bit crowded and I had to go for something small. For those of you who are familiar with software transactional memory, perhaps from working with Clojure or another language that has that, you're not going to be left behind with looks. There is great support for that, and in fact, it can even integrate with the other systems. Like when you commit a STM transaction, it just gives you back a promise that it's going to get the value of the transaction once everything has been committed and all the variables have been modified. And for those of you who are accustomed to working with actors, you will also have this here. You can define all your methods, define what happens when the actor dies, and spawn as many actors as you want. And this is just the concurrency level that is supported right now. There are even more paradigms that are in the pipeline to be added in new releases, and just for the upcoming version 0.6, there will even be agent-based concurrency for those of you who may be familiar with that. Also, of course, looks being a Lisp, it had to have a powerful macro system. But looks' macro system is a little bit different, and I believe a little bit more powerful than what other Lisps provide. In particular, it gives you something that I haven't seen in other languages, which is macros have actual access to the state of the compiler. And this is not some weird marketing gimmick. This isn't a copy of the state. This isn't a view into the state. It is the actual state of the compiler, the very same data structure the compiler uses. So much so that if you were to modify that, you can actually do a lot of really cool things in the compiler by altering its behavior. In this particular example, I actually did something kind of interesting. Basically, it may not look like that from the name of the macro, but basically this implements implicit style polymorphism in looks as a macro. So those of you who are familiar with Scala, you may have already seen that. For those of you who aren't, but maybe you know about Haskell, it's kind of like type classes in the way that you invoke a method and the implementation of the method magically shows up, but basically it takes into account something about the local scope, what particular definitions are visible in a scope, and that's how you control how the polymorphism goes. Basically, in this macro, what I do is that I take in the inputs, the function that you want to invoke, and the arguments that you want to use, and basically it extracts type information for all that stuff from the compiler. It does type checking internally when it looks for the alternative structures that implement the signature that you want, and then if there is a single instance that satisfies your constraints, that's the one that gets inline for you. Something really cool that you can also do with looks macros that other Lisps don't seem to have is monadic parsing of the inputs. So basically, for those of you who may be familiar with common Lisp style macros, like obviously how common Lisp does it and also closure, basically the macro gets the inputs to it as raw AST tokens or raw code tokens. And basically, it is up to you to kind of manually parse what's going on. You have to ask, oh, is this a number? Is this a symbol? Is this whatever? And the problem with that is that that's not really very scalable when you're trying to build like really complicated and powerful macros that maybe require very rich syntax. So the idea, like in this particular macro, I'm using some very, very simple parsing, nothing very special over here. But in general, basically, you have these composable parsers that you can build up. There are parser combinators, and as I said previously, they are monadic, so the level of customizability and power that you can get is actually pretty amazing, and they are reusable. So this is actually very, very nice, because if you're writing a library that involves a lot of macros, you can actually reuse a lot of syntax, and that way you can give your library a very consistent and homogeneous look and feel without actually having to manually replicate all the parsing that you do in each macro. And another really cool feature that I really like is that looks has first-class types. And basically what this means is that types in looks are data structures. Now, for those of you who are familiar with the Lisp way of doing things, this might sound a little bit familiar, because in Lisp, we have this philosophy that code is data and data is code. And basically, this is the same philosophy translated to data types. And what you're actually seeing on the left is actually the type of types. This is actually how you build those type data structures. And the reason why this is interesting is because some of you may be familiar with using types in statically typed languages, but a problem that those languages have is that they impose an artificial barrier between types and values. Basically, you have your types that live over here and your values that live over there, and they don't communicate. There is this small wormhole that connects them called the type checker. But the problem is that only the compiler has access to that. Only the compiler can really see both worlds. As far as the programmer goes, types are just this nice syntactic thing. You write it and it kind of works, but types are not things that you can actually handle. I mean, when was the last time that you actually did type-based computation? When was the last time you pattern matched on a type or you built type at runtime? So basically, the beautiful thing about first-class types is that you build those type data structures, and then you give them to the compiler, and you say, hey, this code over here, this is the expression that computes the type that I want for it. So type check for me. But even though the compiler has access to it, you never lose the access. So you can actually use types at runtime, and you can actually do type-based computation. So on the right side of the slide, there is actually like one of the simplest things that you can do, which is just a small function that, given a list of types, just builds up a tuple type by nesting product types. And this may not seem very impressive, but later on, I'm actually going to show you some really cool examples of things that you can do with this kind of technology. Now, this is all very nice, but cool features don't make a cool language. There has to be something deeper, something fundamental that ties everything together, some vision, some philosophy behind the language. And now I actually want to talk to you about what is the foundation of what I am trying to do with Lux. So one of the things that I want is for Lux to be an omni-platform language. And this actually ties back to what I said previously about Lux targeting multiple platforms like the JVM, Android, and JavaScript. However, I don't want Lux to be multi-platform. I don't want Lux to run in some places and not in others. I want Lux to run everywhere. And the reason is because, personally, I feel some measure of frustration with the current state of the software industry. Like right now, we have a very fragmented model of development. If you want to program in one cell phone, you got to use this language, but another cell phone requires a different language. If you want to run the browser, you got to use JavaScript. The only place where we get variety is like desktop development and server-side, because we have many different languages. But even then, we have constraints. Like if you want to do something like real low level, you got to go with C and C++. Everything else is just not good enough. Basically, what I want is to give people the capacity to do whatever they need in Lux without having to use another languages. Basically because, why is it that we need to relearn the same things every time we need to go to another language? Why is it that we have to keep re-implementing the same libraries and the same frameworks for doing the same things just because we need them to run in different platforms? I want something different for Lux. And I also want Lux to embrace the past. I know that there are many companies that have already made significant investments in other technologies like Java, Python, Ruby, and JavaScript. And I want people to be able to interface with those languages and be able to reuse their investment without having to rewrite everything or having to port things. However, even though I want Lux to run everywhere, I don't want Lux to be constrained by anything. Lux, in a fundamental way, needs to be a platform-independent language. The philosophy is write once, host anywhere. And the reason why I say that is because there have been other languages that have started one place and have tried to go somewhere else. Maybe they started on the JVM and they wanted to go native, or they wanted to go to JavaScript. But a mistake that they always made is that the fundamental semantics of the language got tied up very early on to the first platform where they started. So maybe the semantics of the language is dependent on the JVM or dependent on JavaScript. And what that does is that later, when they want to migrate the language to somewhere else, either they have to replicate the semantics of the host platform somewhere else, which is obviously not always possible, or they basically tell you, hey, this feature, we cannot replicate it somewhere else, so I'm sorry. You are just not going to get it. And as a consequence, when you want to use a library between platforms, you got to ask yourself, is this going to work here? Or did somebody manually port this library to the other place so I can actually reuse it? And it really complicates development. What I want is a no-code change policy for libraries in Lux. Basically, if the library works on the JVM, it has to work completely unmodified on JavaScript, on .NET, and wherever you want to use it. And this doesn't even have to be at the level of libraries. It can even be potentially at the level of programs. Like, imagine the possibility of writing a database engine in Lux, and then you can get it to compile on the JVM, you can get it to compile natively or on .NET, but let's go even crazier. What if you actually want to use it on the browser? All you will need to do is change the underlying storage layer so it uses local storage on the browser or something else to store the data, but the rest of the code is the exact same thing that could be running on the server. The query optimizer, all the machinery, no change necessary. And it may sound really weird, but I actually want to achieve this platform independence without sacrificing access to the host platform and the power that it gives you. Because we programmers have a bit of a pattern for achieving independence. Basically, we just create this nice abstraction layer, and you're supposed to build all your software on top of that, but you're not supposed to ever go beyond the layer. And as a consequence, you end up with this sandbox that gives you independence at the cost of power. Basically, the idea is that the Lux standard library will provide the precise means for interacting with your particular platform, and it will always be tailored to the platform. So there will be a module for specifically doing JVM interrupt, a module for specifically doing JavaScript interrupt. You will not have like a generic FFI layer that kind of works everywhere but has its issues. None of that. You will have all the power without the constraints. And I also want Lux to be a language for deep metaprogramming. And this ties back a lot to its Lisp heritage, but also to what I said before about Lux programs having access to the state of the compiler and types being first-class data structures. So one really cool thing that you can do once you have those two things, access to typing information and being able to do type-based computations, is that you can even implement a type checker in pure Lux. And I actually did that. In the Lux standard library, there is actually a pure Lux implementation of the entire Lux type checker. And this isn't just a gimmick. Like right now, I'm actually in the middle of rewriting the Lux compiler in pure Lux. And the type checker in the compiler is actually going to be the one from the standard library. So that in the future, if you ever use this model, you will actually have the exact same feature set, the exact same correctness that the compiler gets with no difference whatsoever. And with this kind of power, you can implement some really cool stuff. So this ties back to what I talked about before about implicit style polymorphism. So what you have in the example in the middle, well, bottom middle with the functor, basically this is how polymorphism in languages like standard ML kind of works. So basically, you define your polymorphic functions in a signature, but then when you want to use it, you have to actually get the precise structure that implements your signature for your types. However, this can get old pretty fast, especially if you're using methods from the same structures over and over again. You don't want to repeat yourself. So basically, with the power of being able to access types from the compiler and being able to do type checking in pure Lux, I was actually able to implement the implicit style polymorphism macro, which just, it checks your function, it checks your arguments, and it says, okay, what structure I can find that satisfies these constraints, and it just inlines it for you, thereby making polymorphism in Lux far more easy to use. And finally, there is another thing that I want to talk about, which quite sadly, none of the examples that I could get in Lux were small enough to fit in a slide, which is polytypic programming. So for those of you who may not be familiar with this approach, basically, the idea of polytypic programming is that there are algorithms that, if you really think about it, they are not specific to particular types, but rather they are more generic across shapes of types or families of types. So the idea with polytypic programming is that you can define your algorithms based on the primitive elements of what types are made of and how to combine them. And then you provide a particular type and you say, hey, make this algorithm for me, customize it, and then you're basically getting code for free in a type-directed manner. So stuff that you can implement is things like a length or size function, like you can get the length of an array, a list, a set, a hash map, a tree, you can get any kind of thing. Implementations of equality, like what I showed previously on the slide on structures. Let's say that you wrote a backend in Lux or some other type-checked language, but now you have to transmit your data to some JavaScript front end. How will you do that? You're going to turn to JSON. Now, if you're using JavaScript, it's pretty easy, but if you're using another language, you may have to write some function that transforms your data types into JSON. But that's actually a very straightforward thing. It's pretty obvious. So why should we do it? Why can't a machine do it for you? Well, actually, with polytypic programming, you can actually generate binary encodings, JSON encodings automatically in a type-directed fashion. You just give it a type, and you get your code for free. Now, all of these are things that you could have figured out by just checking the Lux repository or even checking the Lux documentation. However, I wanted to make this Strange Loop 2017 talk truly special. So I'm actually going to show you something that I have kept hidden and secret, even from the Loops community, for a few months now, because I wanted to show it to you guys as a Strange Loop exclusive. So pretty soon, Loops is going to become a redefinable language. Now, this sounds really weird. Like, what does it even mean for a language to be redefinable? Well, actually, a few months ago, I was thinking about, what can I do to make Loops even more powerful? What can I do to make Loops transcend what even other languages have been able to accomplish up to this point? And I actually came up with a few interesting observations and ideas. So if you think about it, Lisps have a very well-deserved reputation for being incredibly extensible and customizable. And that is because they have macros, which allow you to extend the syntax of the language, and that way you can really implement some really powerful features that in other languages will be simply impossible. However, even macros have limitations, because ultimately macros must be defined in terms of the fundamental primitives that the language exposes. So what happens when you want to do something that at a fundamental level the language just doesn't allow? Well, the answer is simple. You cannot do it, because there is no way to implement new primitives. There is no way to fundamentally extend the capacity of the language. So what if you could define new primitive functionality just as easily as you can define new macros? Now, this sounds like a really interesting proposal, but how does this even look like? Well, in the same way that you can use macros to extend the syntax of the language, what if you could teach the compiler the meaning of new kinds of expressions? And if you're introducing new kinds of expressions, it makes sense that they're going to be optimized in a different way than everybody else. So why not also teach the compiler how to optimize new kinds of code? And of course, like, even semantics and optimizations have their limits. You still have to work within the constraints of your language. So what if you want to break free of that? What if you want to teach the compiler how to generate new bytecode or new JavaScript code for whatever it is you're trying to create, and escape the boundaries of the language and go directly into the host platform? And all of this as simple as defining macros. But I didn't want to stop there. I want to take things even farther, because with those kinds of extensions, all you do is extend the stages of the compiler. But what if you could reshape the entire compiler as a whole? So Loops compilation looks like compilation for every other language. You do some parsing, some analysis, some optimization, and at the end, you generate some code. But what if you wanted to have, let's say, like really, really, really optimized programs, and you wanted to have even more optimization? You wanted to add extra passes of the compiler into the pipeline. Or maybe you think, you know what? I don't like the Loops type system. It's not rigorous enough for me. I want dependent types. Or maybe you're doing some concurrency and doing some resource handling, and you want linear types for that. Or maybe you don't want types at all, and you just want to have the freedom of dynamic types. Why not be able to change the entire analysis layer for a different one and leave everything else unchanged and have everything work seamlessly? And this can be done to achieve like really amazing things. Like maybe you want to have the same language, the same syntax, same semantics, and the same optimizations, but maybe you don't want Loops to be an eager language. Maybe you love Haskell and you want the same laziness. You could simply change the code generation layer, and now you have laziness for free. Now, it's really nice to talk about all of these features in the abstract, but we are programmers. We solve real problems. So what can you possibly gain from these kinds of features? So actually, I believe you can gain quite a lot. So for instance, something really cool that you can do is introduce platform-specific optimizations into the compiler that are going to be applied pervasively across your program, instead of a per-use basis as we tend to do as programmers. Think about it. Who knows how to make your program faster? Some random guy on the internet writing generic optimizations for programs, or you, who is actually solving a real problem and who actually knows real things about the domain in which you're working? Something that you can also do is bypass Loops' capabilities and introduce new power by accessing the host platform. So maybe the way that you want to achieve higher performance is by introducing SIMD instructions or vector instructions for high parallelism in your programs. But Loops doesn't support that, but who cares? why should you be constrained by what Lux can do? Why can't you just teach the compiler, hey, this kind of code, I want you to use SIMD for it, optimize it for me, and then voila, higher performance. For those of you who are like real fans of hardcore programming and interesting paradigms, you could also use this to efficiently implement new programming paradigms. So maybe you have used Prolog or other logic programming languages, and you want the same thing in Lux. But the problem with encoding one paradigm into another is that there is often overhead. If you have to encode logic programming in functional programming, there is always going to be some inefficiencies because of the encoding and calling a bunch of functions and whatever. What if you could teach the compiler, hey, I know how to compile logic programming code in a fast way. This is how you do it. And not only that, but you can get that while still being able to interface your way of compilation with the rest of the compilation pipeline in Lux, such that your code can interoperate with the rest of the Lux ecosystem. And thereby, you get performance without sacrificing compatibility. Also, something really cool that you can do is transform and instrument Lux programs in a thorough way. So maybe you want to add pervasive logging and tracing for debugging purposes. Or maybe you are a fan of aspect-oriented programming, and you want to add a code weaving layer at the end of the pipeline to perform pervasive transformations across your programs. All of this can be done, or will be doable. And to go even crazier, what about the possibility of even running other languages on top of Lux and having them interoperate? Because if you really think about it, if the entire pipeline can be modified, I can change the parser and thus get a new syntax. I can get new semantics, new optimizations. I could run Python on top of Lux. I could run JavaScript on top of Lux. I could run even new languages on top of Lux. And Lux could end up becoming a platform for polyglot programming in such a way that languages can benefit from the future support for all the platforms that Lux is going to run, and on top of that, work with other languages on top of Lux. So if the same program could have JavaScript code running alongside Python code, running alongside Lux code, and it's just the same program working as a whole. So when can you expect these kinds of features? So for the extensible semantics, optimizations, and code generation, it's actually going to come pretty soon. So the upcoming version of Lux will be 0.6, which is going to come sometime around November, and that's where the first batch of these features is going to come. For the redefinable pipelines, I'm actually going to have to figure a few things out about the design to make sure that it fits well together with all the other features on the compiler. So let's push it a little bit later for version 0.6, sometime mid-2018. Now, I want to stress that this is 21st century programming. For far too long, programmers have been at the mercy of language designers. For far too long, self-styled gurus and experts from the internet have been telling you how to write your code. People who have never taken a look at your code bases or solved your problems are telling you how to do your job. I want to change that. I believe those days are over, and it's finally time to give programmers the capacity to truly shape their technologies based on what they need and what they want. From now on, you will be the master of your own code. From now on, you call the shots. So, where can you learn more? Well, the best place is reading the book. I actually wrote it, and it's always going to be maintained to mirror the current stable release of the language. You don't have to worry necessarily about the URL. You can look it up on Google, Gitbook, Lux programming language, and it's going to show up very fast. And for those of you who want to contribute, please feel free to fork the repo. We're always happy to get new hands. And if you want to say hi and chat with everybody, we actually have a chat room in Gitter, so feel free to come in and say hi. Finally, I want to welcome you to the future, and thank you very much for your attention. So I believe we have a few minutes, so if anybody wants to ask any questions, feel free.
It's really interesting, the idea of adding new primitives to the language. It kind of reminded me of a brackets system for defining languages. Have you looked at that at all?
I've looked a little bit, although I'm not really an expert in Racket. From what I have seen, it seems, maybe I'm wrong about that. Oh, wait, I should have said the question. So basically, he asked about if I had looked at Racket about about implementing new primitives into the language. So basically, what I have seen, it seems, maybe I'm wrong, but what I have seen is more like you can redefine how Racket does a few things, like function application and stuff like that, so that when you run another language on top of that, things are rebound at such a fundamental level that they behave differently. Now, I don't know if that works like in a compile time setting or if it's just like an interpretation thing, but Lux is meant to be a compiled language. So the idea is not to rebound things in a dynamic way so the runtime behaves in a particular way, but teach the compiler, hey, if you're going to run in this particular place, this is what I need you to do to get the features and the performance that I want. So it's all about interfacing with the host platform. Yeah. So basically, the question was how does the feature of the platform portability and the no change policy for Lux libraries is going to work? So basically, there are two particular ways in which I can do that. There is one particular way that has been explored already in Common Lisp and in Closure, which is, for those of you who may be familiar with the closure.cljc files, basically, you provide these snippets of code that say, OK, when you compile to the JVM, do this. When you compile to JavaScript, do that. That is one particular way. However, that is not my favorite way. It's going to be in Lux 0.6 and onwards, but there is another way that actually I'm more interested about, which is the idea of writing platform-specific module implementations. So basically, let's say that you have a file called foo.lux. This is a module in some library, and it's going to expose some features. But there is one particular way of implementing those features on the JVM, and there is a very different way of doing it on JavaScript. So what you can do, or what you will be able to do, because it's actually going to come for version 0.6, is you will be able to have a foo.jvm.lux file and a foo.js.lux file. And for those platforms that don't have the native machinery that you need, but you could possibly emulate it in pure Lux, if you add a normal foo.lux file, that's going to be used as a default in case you don't have a special file. And so the idea is that you can write libraries that depend on platform-specific functionality, but if the host of platforms that you care about all support them in one particular way, you implement that, and then when somebody uses your module, they just call the foo module, and they don't care where it comes from, and then the feature just works. Anybody else? Oh.
Have you thought about tail-call optimization, how you can do that? Some of your platforms, like JVM, don't support full tail-calls.
I'm sorry, please repeat the question.
So you talked about being platform independent. I'm just wondering about features like tail-call optimization, which really need platform support.
OK. So basically, the question was, talking about platform independence in terms of optimizations, how it's done. So basically, in a way, there will be two different kinds of optimizations in Lux. So the Lux pipeline, what it does is that the optimization phase takes your program and basically generates a procedural version of how it works. But it's abstract. It doesn't depend on any one particular platform. The idea being that the code generation layer then interprets that and says, OK, this is the abstract version of how the code is going to run. Let me translate it into the actual JVM version. So in that particular part, those optimizations will always be cross-platform because they don't depend on any particular platform by themselves. As far as optimizations that are platform-specific, you will be able to just introduce them in the code generation layer, but at that point, it's already platform-specific, so there really won't be an issue.
I might be misunderstanding the feature, but you said that you could pattern match on types.
Yes.
So imagine you have like the identity function from A to A. Can you pattern match on what type was in there and then kind of get rid of those guarantees that you have from that polymorphic function? So like for ints, I always return 1 instead of returning back whatever you passed in.
Yeah, actually, let me go to the slide. So actually, all types are modeled as data structures. So in the case of the function from A to A, it would just be an universally quantified type. Like this list of types is just like the environment of the type lambda. So in this case, it will be empty. So basically, it will simply be a universally quantified type where it becomes a function or a lambda type from a bound type 0, which will be the index of the A variable, to the same bound type 0. So yeah, you can just pattern match on it and say, okay, what is this type made of, and what can I do with it? And in fact, several macros in the Lux standard library pattern match on types to generate code of various kinds.
So you would get rid of some of those guarantees that you would really have with polymorphic code by doing that?
If that's what you want, then yeah, sure. How I made the decision to make a typed Lisp or the language in general? A typed Lisp? Okay, well, the question was how I came to the decision of making a typed Lisp. Well, basically, it came out of frustration. So a few years ago, I was actually doing a one-man startup where I was building a product in Clojure, actually. And I'm a big fan of refactoring and polishing my code, and I often found myself like breaking things and spending days like fixing whatever the hell I broke. So my first instinct was actually to use core.type, which is an optional type system in Lux, but in Clojure. But for a few reasons that I'm not gonna get into right now, let's just say that core.type didn't really meet my expectations. And then my instinct was to go to Haskell, because Haskell has great types. But the thing is that I'm a little bit too obsessed with Lisp, so I really couldn't do it. So then I figured out, hey, if I cannot have a Lisp that I need and I cannot have like the types that I need, I'm just gonna put them together and build something for myself. And that's how Lux came into being. Any other question?
So you've done a really good job of making a very enthusiastic pitch. And as someone who's never really worked with compilers before, I'm just sort of curious, which of these features do you think either you like agonize the most over or introduce the most, say, let's say, compiler slowness or misery, and made you say, like, do they really need or want this because it's brutally hard, et cetera, et cetera?
Well, as far as the slow, So basically the question was, these features are nice, but of these features that I'm going to be introducing, which ones will have like the biggest impact on the performance of the compiler?
Not just speed or like complexity, or like hard to maintain the compiler. What hurt the most to add?
Also, what hurts the most to add? Well, basically the pipelines. Because as far as the extensible optimizations, extensible semantics, and code generation, that actually came up while I was doing the rewrite of the compiler into pure Lux. Because I had this concept at a low level in Lux called host procedures, which are basically like functions, but only the compiler knows how they're implemented, and that's how I implemented things like arithmetic and stuff like that, so that higher level code could then invoke it. And while I was doing the rewrite, I actually started grouping those functions in the compiler using a hash map. And then I figured, hey, if I'm using a data structure, then technically these things are dynamic. So why don't I expose plugs for people to start adding stuff? However, that doesn't really like change things like at a very drastic level, because it's basically the same machinery and you're just adding stuff. What could have a bigger impact on the complexity would be the pipelines. And that is actually why it's going to come later in 2018, because I actually needed to get it to work with some of the important features of the compiler, like parallel compilation and the caching that the compiler does, and that can get a little bit tricky. So that will be the most complicated thing. So I think we're already out of time, and so if anyone has more questions, then feel free to grab me afterwards. Thank you very much.